You gave me an amazing tour of Blue Origin rocket factory and launch complex in the historic Cape Canaveral. That's where New Glenn, the big rocket we talked about, is being built and will launch. Can you explain what the New Glenn rocket is and tell me some interesting technical aspects of how it works?
Sure. New Glenn is a very large, a heavy lift launch vehicle. It'll take about 45 metric tons to LEO, very large class. It's about half the thrust, a little more than half the thrust of the Saturn V rocket. So it's about 3.9 million pounds of thrust on liftoff. The booster has 7 BE4 engines. Each engine generates a little more than 550,000 pounds of thrust. The engines are fueled by liquefied natural gas, LNG, as the fuel, and LOX as the oxidizer. The cycle is an Ox-rich stage combustion cycle. It's a cycle that was really pioneered by the Russians. It's a very good cycle. And that engine is also going to power the first stage of the Vulcan rocket, which is the United Launch Alliance rocket. Then the second stage of New Glenn is powered by 2 BE3U engines, which is a upper stage variant of our New Shepard liquid hydrogen engine. So the BE3U has 160,000 pounds of thrust. So 2 of those, 320,000 pounds of thrust. And hydrogen is a very good propellant for upper stages because it has very high ISP. It's not a great propellant, in my view, for booster stages because the stages then get physically so large. Hydrogen has very high ISP, but liquid hydrogen is not dense at all. So to store liquid hydrogen, if you need to store many thousands of pounds of liquid hydrogen, your liquid hydrogen tank gets very large. So you get more benefit from the higher ISP, the specific impulse. You get more benefit from the higher specific impulse on the second stage. And that stage carries less propellant, so you don't get such geometrically gigantic tanks. Mm-hmm. The Delta IV is an example of a vehicle that is all hydrogen. The booster stage is also hydrogen. Mm-hmm. And I think that it's a very effective vehicle, but it never was very cost effective. So it's operationally very capable, but not very cost effective.
So size is also costly.
Size is costly. So it's interesting. Rockets love to be big. Mm-hmm. Everything works better.
What do you mean by that? You've told me that before. It sounds epic, but what was it?
I mean, when you look at the kind of the physics of rocket engines, and also when you look at parasitic mass, it doesn't. If you have, let's say you have an avionics system, so you have a guidance and control system, that is going to be about the same mass and size for a giant rocket as it is going to be for a tiny rocket. Mm-hmm. And so that's just parasitic mass that is very consequential if you're building a very small rocket, but is trivial if you're building a very large rocket. So you have the parasitic mass thing. And then if you look at, for example, rocket engines have turbopumps. They have to pressurize the fuel and the oxidizer up to a very high pressure level in order to inject it into the thrust chamber where it burns. And those pumps, all rotating machines, in fact, get more efficient as they get larger. So really tiny turbopumps are very challenging to manufacture, and any kind of gaps, are like between the housing, for example, and the rotating impeller that pressurizes the fuel. There has to be some gap there. You can't have those parts scraping against one another. Mm-hmm. And those gaps drive inefficiencies. And so, if you have a very large turbopump, those gaps in percentage terms end up being very small. And so there's a bunch of things that you end up loving about having a large rocket, mm-hmm. and that you end up hating for a small rocket. But there's a giant exception to this rule, and it is manufacturing. So manufacturing large structures is very, very challenging. It's a pain in the butt. And so, it's just, if you're making a small rocket engine, you can move all the pieces by hand. You can assemble it on a table. One person can do it. You don't need cranes and heavy lift operations and tooling and so on and so on. When you start building big objects, infrastructure, civil infrastructure, just like the launch pad and all this. We went and visited. I took you to the launch pad, and you can see it's so monumental.
Yeah, it is.
And so just these things become major undertakings, both from an engineering point of view, but also from a construction and cost point of view.
And even the foundation of the launch pad. I mean, this is Florida. Like, isn't it like swampland? Like, how deep you have to go?
At Cape Canaveral.
Yeah.
In fact, at most ocean, most launch pads are on beaches somewhere in the ocean side because you want to launch over water for safety reasons. Yes, you have to drive pilings, dozens and dozens and dozens of pilings, 50, 100, 150 feet deep to get enough structural integrity for these very large, yes, these turn into major civil engineering projects.
I just have to say, everything about that factory is pretty badass. You said tooling. The bigger it gets, the more epic it is.
It does make it epic.
Yeah.
It's fun to look at. It's extraordinary.
It's humbling also because your humans are so small compared to it.
We are building these enormous machines that are harnessing enormous amounts of chemical power, in very, very compact packages. It's truly extraordinary.
But then there's all the different components, and the materials involved. Is there something interesting that you can describe about the materials that comprise the rocket? So it has to be as light as possible, I guess, whilst withstanding the heat and the harsh conditions.
Yeah, I play a little kind of game sometimes with other rocket people that I run into where say, what are the things that would amaze the 1960s engineers?
Mm-hmm.
Like what's changed? Because surprisingly, some of rocketry's greatest hits have not changed. They would recognize immediately a lot of what we do today, and it's exactly what they pioneered back in the 60s. But a few things have changed. The use of carbon composites is very different today. We can build very sophisticated. You saw our carbon tape laying machine that builds the giant fairings, and we can build these incredibly light, very stiff fairing structures out of carbon composite material that they could not have dreamed of. I mean, the efficiency, the structural efficiency of that material is so high compared to any, metallic material you might use or anything else. So that's one. Aluminum lithium and the ability to friction stir weld aluminum lithium. Do you remember the friction stir welding that I showed you? This is a remarkable technology. It was invented decades ago, but has become very practical over just the last couple of decades. And instead of using heat to weld two pieces of metal together, it literally stirs the two pieces. There's a pin that rotates at a certain rate, and you put that pin between the two plates of metal that you want to weld together, and then you move it at a very precise speed. And instead of heating the material, it heats it a little bit because of friction, but not very much. You can literally immediately after welding with stir friction welding, you can touch the material and it's just barely warm. It literally stirs the molecules together. It's quite extraordinary.
Relatively low temperature, and I guess high temperature is what makes them that makes it a weak point.
Exactly. So with traditional welding techniques, you may have whatever the underlying strength characteristics of the material are. You end up with weak regions where you weld. Mm-hmm. And with friction stir welding, the welds are just as strong as the bulk material. So it really allows you, and so because when you're, let's say you're building a tank that you're going to pressurize, a large, liquid natural gas tank for our booster stage, for example, if you are welding that with traditional methods, you have to size those weld lands, the thickness of those pieces, with that knockdown for whatever damage you're doing with the weld, and that's going to add a lot of weight to that tank.
I mean, even just looking at the fairings, the result of that. the complex shape that it takes, and
Yeah.
and like what it's supposed to do is kind of incredible because so people don't know it's on top of the rocket. It's going to fall apart. That's its task, but it has to stay strong sometimes,
Yes.
and then disappear when it needs to.
That's right.
Which is a very difficult task.
Yes. When you need something that needs to have 100% integrity until it needs to have 0% integrity, it needs to stay attached until it's ready to go away. And then when it goes away, it has to go away completely. You use explosive charges for that. And so it's a very robust way of separating structure when you need to.
Exploding.
Yeah. Little tiny bits of explosive material, and it'll sever the whole connection.
So if you want to go from 100% structural integrity to 0 as fast as possible, is explosives.
Use explosives.
The entirety of this thing is so badass. Okay, so we're back to the 2 stages. So the first stage is reusable.
Yeah. Second stage is expendable. Second stage is liquid hydrogen, liquid oxygen. So we get to take advantage of the higher specific impulse. The first stage lands downrange on a landing platform in the ocean, comes back for maintenance and get ready to do the next mission.
I mean, there's a million questions, but also, is there a path towards reusability for the second stage?
There is, and we know how to do that. Right now, we're going to work on manufacturing that second stage to make it as inexpensive as possible. There's sort of 2 paths for a second stage. Make it reusable, or work really hard to make it inexpensive so you can afford to expend it. And that trade is actually not obvious which one is better.
Even in terms of cost, even like time,
even in
cost,
terms of, and I'm talking about cost. Space flight, getting into orbit is a solved problem. We solved it back in the 50s and 60s.
You're making it sound easy.
The only interesting problem is dramatically reducing the cost of access to orbit, which is, if you can do that, you open up a bunch of new endeavors that lots of startup companies, everybody else can do. So that's one of our missions, is to be part of this industry and lower the cost to orbit so that there can be a kind of a renaissance, a golden age of people doing all kinds of interesting things in space.
I like how you said getting to orbit is a solved problem. It's just the only interesting thing is reducing the cost. You can describe every single problem facing human civilization that way. The physicists would say everything is a solved problem. We've solved everything. The rest is just what Rutherford said, that it's just stamp collecting. It's just the details. Some of the greatest innovations and inventions and brilliance is in that cost reduction stage, right? And you've had a long career of cost reduction
for sure. And if what does cost reduction really mean? It means inventing a better way.
Yeah, exactly.
Right. And when you invent a better way, you make the whole world richer. So, whatever it was, I don't know how many thousands of years ago, somebody invented the plow. Mm-hmm. And when they invented the plow, they made the whole world richer because they made farming less expensive. And so it is a big deal to invent better ways. That's how the world gets richer.
So what are some of the biggest challenges on the manufacturing side, on the engineering side that you're facing in working to get to the first launch of New Glenn?
The first launch is one thing, and we'll do that in 2024, coming up in this coming year. The real thing that's the bigger challenge is making sure that our factory is efficiently manufacturing at rate. So rate production. So consider if you want to launch New Glenn, 24 times a year, you need to manufacture a upper stage, since they're expendable, every, twice a month. You need to do one every 2 weeks. So you need to have all of your manufacturing facilities and processes and inspection techniques and acceptance tests and everything operating at rate. And rate manufacturing is at least as difficult as designing the vehicle in the first place. Mm-hmm. And the same thing. So every every upper stage has 2 BE3U engines. So those engines, you need, if you're going to launch the vehicle twice a month, you need 4 engines a month. So you need an engine every week. So that engine needs to be being produced at rate. And that's and there's all of the things that you need to do that, all the right machine tools, all the right fixtures, the right people, process, etc. So it's one thing to build a first article, right? So that's, to launch New Glenn for the first time, you need to produce a first article. But that's not the hard part. The hard part is everything that's going on behind the scenes to build a factory that can produce New Glens at rate.
So the first one is produced in a way that's enables the production of the second, the third, and the fourth, and the fifth, and sixth.
You could think of the first article as kind of pushing it. It pushes all of the rate manufacturing technology along. In other words, it's kind of the it's the test article in a way that's testing out your manufacturing technologies.
The manufacturing is the big challenge.
Yes. I mean, I don't want to make it sound like any of it is easy. I mean, the people who are designing the engines and all this, all of it is hard, for sure. But the challenge right now is driving really hard to get to rate manufacturing, and to do that in an efficient way. Again, kind of back to our cost point. If you get to rate manufacturing in an inefficient way, you haven't really solved the cost problem, and maybe you haven't really moved the state of the art forward. All this has to be about moving the state of the art forward. There are easier businesses to do. I always tell people, look, if you are trying to make money, like start a salty snack food company or something. You
write that idea down.
Like make the Lex Fridman potato chips.
Don't say it. People are going to steal it. But yeah, it's hard.
You see what I'm saying? It's like there's nothing easy about this business, and but it's its own reward. It's fascinating. It's worthwhile. It's meaningful. And so, I don't want to pick on salty snack food companies, but I think it's less meaningful. At the end of the day, you're not going to have accomplished something amazing.
Yeah,
even if you do make a lot of money at it.
Yeah, there's something fundamentally different about the quote unquote business of space exploration.
Yeah, for sure.
It's a grand project of humanity.
Yes, it's one of humanity's grand challenges. And especially as you look at going to the moon and going to Mars and building giant O'Neill colonies and unlocking all the things, I won't live long enough to see the fruits of this. But the fruits of this come from building a road to space, getting the infrastructure. I'll give you an analogy. When I started Amazon, I didn't have to develop a payment system. It already existed. It was called the credit card. I didn't have to develop a transportation system to deliver the packages. It already existed. It was called the Postal Service and Royal Mail and Deutsche Post and so on. So all this heavy lifting infrastructure was already in place, and I could stand on its shoulders. And that's why when you look at the internet, by the way, another giant piece of infrastructure that was around in the early, I'm taking you back to like 1994, people were using dial-up modems, and it was piggybacking on top of the long distance phone network. That's how the internet, that's, how people were accessing servers and so on. And that, again, if that hadn't existed, it would have been hundreds of billions of capex to put that out there. No startup company could have done that. And so the problem, you see if you look at the dynamism in the internet space over the last 20 years, it's because, you see like 2 kids in a dorm room could start an internet company that could be successful and do amazing things because they didn't have to build heavy infrastructure. It was already there. And that's what I want to do. I'd take, my Amazon winnings and use that to build heavy infrastructure so that the next generation, the generation that's my children and their children, these, those generations can then use that heavy infrastructure. Then there'll be space entrepreneurs who start in their dorm room.
Yeah.
Like that will be a marker of success. when you can have a really valuable space company started in a dorm room, then we know that we've built enough infrastructure so that ingenuity and imagination can really be unleashed. I find that very exciting.
As they will, of course, as kids do, take all of this hard infrastructure building for granted.
Of course,
Which
that's
is the entrepreneurial spirit.
That's an inventor's greatest dream.
Yeah.
Is that their inventions are so successful that they are one day taken for granted. Nobody thinks of Amazon as an invention anymore. Nobody thinks of customer reviews as an invention. We pioneered customer reviews, but now they're so commonplace. Same thing with one-click shopping and so on.
Yeah.
But that's a compliment. That's how, you invent something that's so used, so beneficially used by so many people that they take it for granted.
I don't know about nobody. Every time I use Amazon, I'm still amazed. How does this work? The logistics.
That proves you're a very curious explorer.
All right. Back to rockets. Timeline. You said 2024. As it stands now, are both the first test launch and the launch of Escapade Explorers to Mars still possible
in 2024?
Yeah.
Yeah, I think so. For sure, the first launch, and then we'll see if Escapade goes on that or not. I think that the first launch for sure, and I hope Escapade too.
Hope?
Well, I just don't know which mission it's actually going to be slated on.
Sure.
So we also have other things that might go on that first mission.
Oh, I got it. But you're optimistic that the launches will still...
Oh, the first launch, I'm very optimistic that the first launch of New Glenn will be in 2024, and I'm just not 100% certain what payload will be on that first launch.
Are you nervous about it?
Are you kidding? I'm extremely nervous about it.
Oh, man.
100%. I've, every launch I go to, for New Shepard, for other vehicles too, I'm always nervous for these launches. But yes, for sure. A first launch, to have no nervousness about that would be, some sign of derangement, I think. So,
well, I got to visit the launch pad. It's pretty, it's epic.
We have done a tremendous amount of ground testing, a tremendous amount of simulation. So, a lot of the problems that we might find in flight have been resolved, but there are some problems you can only find in flight. So, cross your fingers. I guarantee you'll have fun watching it no matter what happens.
100%. When the thing is fully assembled and comes up.
Yeah, the transporter erector, the transporter erector for a rocket of this scale is extraordinary.
That's an incredible machine.
The vehicle travels out horizontally and then kind of comes up in
over a few hours.
Beautiful. Yeah, it's a beautiful thing to watch.
Speaking of which, if that makes you nervous, I don't know if you remember, but you were aboard New Shepard on its first crewed flight. How was that experience? Were you terrified then?
Strangely, I wasn't.
You ride the rocket.
It's
less nerve-wracking.
True.
Okay.
I've watched other people ride in the rocket, and I'm more nervous than when I was inside the rocket myself. It was a difficult conversation to have with my mother. When I told her I was going to go on the first one. Yeah. And not only was I going to go, but I was going to bring my brother too. This is a tough conversation to have with a mom. And
there's a long pause. You told her.
She's like, both of you? And it was an incredible experience. And we were laughing inside the capsule, and, we're not nervous. The people on the ground were very nervous for us. It was actually one of the most emotionally powerful parts of the experience. It happened even before the flight. At 4:30 in the morning, brother and I are getting ready to go to the launch site, and Lauren is going to take us there in her helicopter, and we're getting ready to leave. And we go outside the ranch house there in West Texas, where the launch facility is. And all of our family, my kids and my brother's kids, and our parents and close friends are assembled there, and they're saying goodbye to us. But they're kind of saying, maybe they think they're saying goodbye to us forever.
Mhm.
And, we might not have felt that way, but it was obvious from their faces how nervous they were that they felt that way. And it was sort of powerful because it allowed us to see, it was almost like attending your own memorial service or something. Like you could feel how loved you were in that moment. And it was really amazing.
Yeah, and I mean, there's just a epic nature to it too.
The ascent, the floating in zero gravity, I'll tell you something very interesting. Zero gravity feels very natural. I don't know if it's because we're, it's like
I-
return to the womb.
You just
or
confirmed
what it
you're an
is.
alien, but that's I think that's what you just said.
It feels so natural to
Yeah.
be in zero G. It was really interesting. And then
Hmm.
what people talk about, the overview effect and seeing Earth from space, I had that feeling very powerfully. I think everyone did. You see how fragile the Earth is. If you're not an environmentalist, it will make you one. The great Jim Lovell quote, he looked back at the Earth from space and he said he realized you don't go to heaven when you die, you go to heaven when you're born. And it's just, that's the feeling that people get when they're in space. You see all this blackness, all this nothingness, and there's one gem of life, and it's Earth.
It is a gem. You've talked a lot about decision making throughout your time with Amazon. What was that decision like to be the first to ride New Shepard? Like what? Just before you talk to your mom,
Yeah.
what the pros and cons? Like actually, as one human being, as a leader of a company, on all fronts, like what was that decision making like?
I decided that, first of all, I knew the vehicle extremely well. I know the team who built it. I know the vehicle. I'm very comfortable with the escape system. We put as much effort into the escape system on that vehicle as we put into all the rest of the vehicle combined. It's one of the hardest pieces of engineering in the entire New Shepard architecture.
Can you actually describe what do you mean by escape system? What's involved?
We have a solid rocket motor in the base of the crew capsule so that if anything goes wrong on ascent, while the main rocket engine is firing, we can ignite this solid rocket motor in the base of the crew capsule and escape from the booster. It's a very challenging system to build, design, validate, test, all of these things. It is the reason that I am comfortable letting anyone go on New Shepard. So the booster is as safe and reliable as we can make it. But we're harnessing, whenever you're talking about rocket engines, I don't care what rocket engine you're talking about, you are harnessing such vast power in such a small, compact geometric space. The power density is so enormous that it is impossible to ever be sure that nothing will go wrong.
Mhm.
And so the only way to improve safety is to have an escape system. And historically, human-rated rockets have had escape systems. Only the space shuttle did not. And but Apollo had one. All of the previous, Gemini, etc. They all had escape systems. And we have on New Shepard unusual escapes. Most escape systems are towers. We have a pusher escape system. So the solid rocket motor is actually embedded in the base of the crew capsule and it pushes. And it's reusable in the sense that if we don't use it, so if we have a nominal mission, we land with it. The tower systems have to be ejected at a certain point in the mission. And so they get wasted even in a nominal mission. And so again, cost really matters on these things. So we figured out how to have the escape system be a reusable, in the event that it's not used, you can reuse it, and have it be a pusher system. It's a very sophisticated thing. So I knew these things. You asked me about my decision to go. And so I know the vehicle very well. I know the people who designed it. I have great trust in them and in the engineering that we did. And I thought to myself, look, if I am not ready to go, then I wouldn't want anyone to go. A tourism vehicle has to be designed, in my view, to be as safe as one can make it. You can't make it perfectly safe. It's impossible. But, you just have to, people will do things, people take risk, they climb mountains, they skydive, they, do deep underwater scuba diving and so on. People are okay taking risk. You can't eliminate the risk, but it is something, because it's a tourism vehicle, you have to do your utmost to eliminate those risks. And I felt very good about the system. I think it's one of the reasons I was so calm inside, and maybe others weren't as calm. They didn't know as much about it as I did.
Who was in charge of engaging the escape system? Did you have?
It's automated.
Okay.
The escape system is completely automated. Automated is better because it can react so much faster.
Yeah. So yeah, for tourism, rockets, safety is a huge priority. For space exploration also, but a tiny, a delta less.
Yes. I mean, I think if you're doing, there are human activities where we tolerate more risk. If you're saving somebody's life, if you are, engaging in real exploration, these are things where, I personally think we would accept more risk, in part because you have to.